right. So as I said earlier, we've talked about how you get packets from A to B in a Kubernetes infrastructure, which is great. These environments are not going to work without networking between the pods, because we always talk about microservices, services that consume other services, etc. We need network connectivity. However, that comes at a potential risk in that if I have unfettered connectivity between all of these individual endpoints in a Kubernetes infrastructure, and there might be tens or hundreds of thousands of pods in a large Kubernetes deployment, I have a huge ability for someone to come along and make what's called lateral movement across the infrastructure. So if I think of the environment that we're talking about, let's just take a really simple case of I've got some number of pods. I'll just draw 5. I don't feel like drawing 50,000, but call me lazy. So I'll draw 5 pods. And let's say these 5 pods are at least partially active in a given application. They might be other applications that draw. In fact, I'll draw 2 applications. So I've got the red application, and the red application needs network connectivity going that way, and it has network connectivity going that way, and this is the inbound to that application. Similarly, I might have another application where this application needs connectivity there and needs connectivity there. So for whatever I'm doing, I have 2 applications, the red and the green, and this is what we call the service graph, or the application graph that's necessary. So we need to make sure this works, otherwise the applications don't work. However, there are a lot more connections possible. Drawing them out, I have this connection, which isn't being used. I have this connection. I have this connection, which isn't being used. I have that connection, which isn't being used. That connection, which isn't being used. That connection, which isn't being used. This connection, which isn't being used. And this connection, which isn't being used. This connection, which isn't being used. And this connection, which isn't being used. So I should have picked a color other than yellow and green, but forgive me. But you'll see the vast majority of connections here aren't actually being used, but they're still available because we have connectivity between all our pods. Which basically means, especially if I look at this one, if someone was able to hijack this pod, I'm not going to draw the skull and crossbones because I'm not that good an artist, but let's say somebody were to hijack that pod. From this point, they can connect to all of the other pods and explore for weaknesses. This is called reconnoitering. Find where the interesting data sets are and exfiltrate them. Similarly, if I end up here and I hijack this, and the red application isn't really all that sensitive, but I can talk to this, or I can talk to this pod, and that pod does have sensitive data, I can talk to it and I can exfiltrate it out. Maybe this is the one that has external access anyway, so that's easy. So I've now created a very large attack surface on circuits that I'm not using, which means I'm probably not really looking at them all that hard, right? if I don't use this, I'm not watching it, I'm not checking for defects, etc. on it because my applications don't use it. But it certainly could be used for nefarious purpose. So what we need to do is build, for all intents and purposes, a set of firewalls that block this. And the reason we do that is something called zero trust networking, or concept of least privilege, which basically says that I should only allow connections that theoretically, or actually more than theoretically, in reality are necessary for the applications to work. I should not allow these yellow lines to exist. The only connections that should exist are the blue, or the green, and the red lines. All other connections should be blocked. That's the concept of least privilege, which is a key part of something called zero trust networking, which we're going to talk about later in the series. So now, how do we do this? Traditionally, we do this by setting up firewalls. Set firewalls between my front end and my middleware and my database, or I set firewalls on the perimeter. And most traffic was north-south, so you could do that. You could create those trust boundaries, sort of like a circle of trust, right? You could say, you could build a, here's my untrusted edge. Lots of stuff goes on in there. And then in the middle of that, I build my next ring of defense. And I have firewalls that only allow certain things to go from green to yellow ring. And then similarly, I have other firewalls that exist that control traffic from the yellow ring to the red ring. This is the ring model. We do this a lot with firewalls. Sometimes they're layers, but it's still a ring model. So we've been doing that a lot in the industry. There's a bit of a problem with this. Pod lifetimes are very, very short. Pods may only last for seconds, minutes, hours, maybe a couple days. And pods constantly are changing as far as the number of pods. If you set Kubernetes to auto-scale your application, as this pod gets busier, Kubernetes is going to stamp more instances of this pod. Each of those have their own address. When you update a pod because of a vulnerability or a code change, that pod goes away. Another pod of the new version type gets stood up. It gets a different address. The address that was used on this pod, which is no longer there, is now used for another instance of this pod when it gets life cycled. So IP addresses are ephemeral, and IP addresses aren't tied to a thing like application A database. An IP address is just a physical network address or a logical network address for a pod. It has no meaning as to what that pod is. Since firewalls use IP addresses as a proxy for what something is, we have a problem. So if I have a firewall that says this thing should only allow red flows here, and that's tied to this IP address, then I life cycle this, and this goes away, and I now have a version prime of this pod. Guess what? Address is not equal address prime. So this address is no longer what's used to identify this. At some point later in time, this, which is say B, gets life cycled and becomes B prime. But B prime actually happens to be the same address as A. Now I have a big problem because I have granted this thing the privileges of this pod because the IP addresses are the same even though the pods are different. Or again, if Kubernetes all of a sudden stands up, N of these because of load balancing, etc., I now end up with lots of these things all having unique addresses. And no human's been involved in this process. So I have no way of putting a catch in there and saying I need to change my firewall rules, even if I could change my firewall rules in short order, which in most cases you can't. So this presents a problem, and Kubernetes network policy is the answer to this problem. The team here at Project Calico and at Tigera was fairly influential in creating the Kubernetes network policy model, along with a lot of other people in the community as well. But we're going to talk about Kubernetes network policy and how this problem is solved. So, as we just saw, there's an inherent problem with using IP-based firewalls the way we've usually used them in a Kubernetes environment. The IP address environment is just too dynamic. So, what a lot of people have done when they started standing up Kubernetes clusters is they've either isolated the entire cluster and or they've driven a firewall around the perimeter and assumed that everything inside that perimeter, so perimeter-based firewalling, is trusted, secure, and sanitary. None of that is true, or very likely to stay true for long. Those firewalls protect one mode of ingress. There are lots of other modes of ingress. So you think about it, you've locked the front door, but your back windows are still there, and the garage is still unlocked, etc. So that might be someone socially engineering to get credentials to be able to launch pods in your infrastructure. That might be someone subverting something upstream of you, and you pull